In this lecture, we will be discussing about the Perceptron convergence theorem. To derive the error correction learning algorithm for the perceptron, let us consider the signal flow graph of the perceptron, which is like this. Here we have inputs x1, x2, so on up to xm, and the corresponding weights w1 to wm, and we also have a fixed input which is given by x0 is equal to 1, and the corresponding weight is given by the bias. So the input vector can now be given as x of n is equal to plus 1, which is a fixed input, and then x1 of n, x2 of n, so on up to xm of n whole transpose, and w of n is given by the first weight, the bias, which is the weight for this fixed input, and then w1 of n for x1 of n, and w2 of n for x2 of n, and so on up to wm of n for xm of n whole transpose. So this is the output V, which is given by V of n after representing the nth pattern of the input, which is given by sigma I equal to 0 to m wi of n into xi of n. So which in turn is given by the wt of n into x of n, where this wt of n is the transpose of the weight vector and this x of n is the input vector. Next, the v is given to phi v, which is the hard limiter, wherein this hard limiter is going to transform the value of v into the output. So the output y is given by phi of v. So this we have already discussed in the previous sessions, right? So now after completing the representation of the signal flow graph of the simple perceptron, we now let us go to the two class pattern classification problem. Here we have two classes. The first one is class C1 and the second one is class C2, where these two classes are linearly separable classes. So we already discussed what are linearly separable classes also. Let us now say that this is the set C1, that is, this is the set represented by class C1, and these set of patterns belongs to class C2. So if we draw a straight line between these two classes, so obviously this straight line makes these two classes linearly separable. That is, there is a clear distinction between the class C1 and class C2, so that these two classes can now be called as linearly separable classes, and these patterns are called linearly separable patterns. So here simply we have represented with a straight line, but this actually will be a hyperplane. This is the decision boundary. So the decision boundary should lie at the value v equal to 0. So what is the value of v here? W transpose of n into x of n. So this value should be equal to 0. That is, the equation of the hyperplane of the decision boundary must be equal to 0. So that is the reason we have represented this hyperplane with wt, that is w transpose into x is equal to 0. So in this case, these two classes are linearly separable. But if you consider another case, so this is class C1 and this is class C2. So these two classes, that is the patterns in this class and the patterns in this class, are not linearly separable. That is, these are non-linearly separable patterns. So always we cannot say that we will be having all the linearly separable patterns. So this we cannot draw a straight line between these two classes. So this is an example of a non-linearly separable patterns. So if we discuss about these two classes, so any input pattern we take or any input vector we take from the m dimensional space, it either should be belonging to class C1 or it should be belonging to class C2. And in order to train this perceptron, if you see here, in order to train this perceptron, we have to take the set of patterns, right? That is, we have to train the perceptron with sufficient number of patterns that are taken from the class C1 and the class C2. So for the training purpose, we take H1 as a training set, where this H1 belongs to class C1. and H2 as the training set which belongs to class C2. So our total training patterns are class H, where this H1 and H2, the union of these H1 and H2 patterns will give us H. That is, the H1 training patterns are subset of class C1 and the H2 training patterns are subset of class C2. So we make clear that we are not taking every sample of this particular class C1, right? So we are taking only some samples. So we represent those samples as H1. So obviously H1 is a subset of C1 and H2 is a subset of class C2. We can now write the classification equation given that the decision boundary is given with the help of this equation W transpose into X equal to 0. So we can now definitely write that the first one, W transpose into X, is greater than 0 for every input vector X belongs to class C1, and W transpose this X vector is less than or equal to 0 for every input vector X belongs to C2. So this line says that the W transpose X is less than or equal to 0. So here it says that the input vector X belongs to the class C2 if the W transpose X is equal to 0. So this generally depends upon how we are going to take. So now the classification which is done by the network can be either right or wrong. That is, if the input vector X is belonging to the class C1, so then obviously W transpose X is greater than 0. That is, if we say that the input vector X belongs to C1 and if we get W transpose X is greater than 0, so obviously the classification is correct, right? So if the classification is right, then there is no problem. That is, then there is no reason for us to change the weights. That is, we need not change any weights. So let us consider another case where we take the input pattern from the class H2. So obviously this pattern belongs to class C2, but even though it belongs to class C2, actually the W transpose X value must be less than or equal to 0. But if you take a pattern from H2 which is obviously belonging to C2, but if its W transpose X value is greater than 0, obviously it is wrong. So here at this moment of time we need the updation of weights. So for this reason we will see the weight updation algorithm, that is how we are going to update the weights of our perceptron. So the first step in the weight updation algorithm is, if a particular input belongs to class C1 and the W transpose X value is greater than 0, obviously it is a correct classification, right? Then as already said, there is no need of changing the weights, right? That is, the Wn plus 1 vector is equal to W of n. That is, there is no change in weights. That is, the updated weight is equal to the previous weight. And in the same thing, if an input pattern X of n is belonging to the class C2 and if W transpose X of n is less than or equal to 0, so at this moment of time also there is no need of change in weights. So that is the reason we have W of n plus 1, that is the updated weight is equal to the previous weight. So this is the correct classification. So in case of correct classification, there is no need for us to update the weights. So now let us see the second case, where if the input vector X of n belongs to class C2. So if it belongs to class C2, what is our condition? W transpose X must be less than or equal to 0. But here we got the W transpose of n into X of n as greater than 0. So now what we have to do? Obviously we have to update the weight. So now the new weight given by W of n plus 1 is the previous weight W of n minus eta into X of n. So for the same thing, if the input vector X of n belongs to class C1 and if W transpose n into X of n is less than or equal to 0, obviously at this condition also we have to update the weights. That is, W of n plus 1 is equal to W of n plus eta into X of n. So we may get it out that how we have taken the minus here and plus here. So generally the hyperplane is shifting from one place to another place. That is, it is the actual boundary between these two classes. So the hyperplane could be at this place, or the hyperplane can be at this place. That is, it could be shifted from either this place to this place. So as accordingly, we have to take the minus or plus here. So after completing this weight updation algorithm, let us now go to the proof of convergence. To present the proof of convergence, so there are some initial assumptions we are assuming. Don't think that these assumptions are directly affecting the result, but there is one assumption which directly affects the result, that is linear separability. Obviously, if this assumption, that is linear separability, is violated, we cannot use the perceptron for pattern classification problem. So linear separability is the essential criteria. So the assumptions we are making for the ease of mathematical computation are as follows. The first one is linear separability, as already discussed, and the second assumption is W of 0 is equal to 0. That is, the weight vector we are using initially is a 0 vector. Initially we are assuming all the weights to be equal to 0. The third assumption is eta is equal to 1. In the previous classes itself, we learned that taking the smaller value of eta will make the network obviously converge. That is, it may take more amount of time to converge, but we guarantee that the network is going to converge, right? So here we are taking a larger value of eta, that is eta is equal to 1. So if we prove that the network is going to converge for the value of eta is equal to 1, but generally our eta value lies between 0 and 1. So obviously we can prove that for all the values which are lying between 0 and 1 also, the network is going to converge. Let us suppose now that we feed the patterns x of n and n values ranging from 1 to so on up to n. And initially let us say that the network is doing the misclassification. So to start with, the network, let us assume that the network does the misclassification when we are giving n is equal to 1, that is x1, x2 and so on. So by doing the misclassification itself, we can say that now the network is starting to learn from this misclassification. But the thing is that if it is convergent, there should be some value of n where we are going to get the correct classification. Let us assume that the xn belongs to the subset h1, that is this must be classified into the class C1 and eta equal to 1. So as initially assumed that we assume that this is misclassified. So what will be our Wn plus 1? So in the previous equation, class C1, W of n plus 1 equal to W of n plus eta into x of n. So here we have got W of n plus 1 equal to W of n plus eta into x of n. So we already assumed that the eta value is 1. So now it will become W of n plus x of n. Let us assume that this is an equation A. So from our initial assumption, as we have already taken W of 0 is equal to 0, right? So now we put this W of 0 value equal to 0 for n equal to 0. So put n equal to 0 here. Now what will be this? So W of 0 plus 1, which is nothing but W of 1 is equal to W of 0 plus x of 0, right? So what is the value of W of 0 from our assumption? It is 0. So now this W of 1 will be so x of 0. See, because W of 0 is 0, so now W of 1 will be x of 0. Similarly, what is W of 2? W of 2 will be, so from this W of 2 will be W of 1 plus x of 1. So this is W of 1 plus x of 1. So what is W of 1 value we got? X of 0. That is x of 0 plus x of 1. So while we continue the value of 1 to so on, so now we will be ultimately getting W of n plus 1 is equal to x of 0 plus x of 1 plus so on up to x of n. Let us assume that this is equation 1. So here actually we are considering x of 0 plus x of 1 so on up to x of n, but we do not consider x of 0 while solving the equations because this is a fixed input, right? So here we have used this assumption, that is W of 0 equal to 0 and eta is equal to 1. And the third assumption we had is the classes C1 and C2 are linearly separable. So far, although we have assumed that the network is doing the misclassification. So till now we have assumed that the network is doing misclassification, right? The solution obviously exists, that is, the solution exists, but till now we have not reached to a point where we find our solution. So because we can find a solution, hence a solution W0 exists for which W naught transpose x of n is greater than 0 for x of 1 comma x of 2 comma so on up to x of belongs to h1, which means the solution W0 definitely exists, which does the correct classification, because we already know that if the input vector x belongs to class C1, then W transpose x will be greater than 0. So obviously we thought that here the W transpose x of n is greater than 0, indicating that a solution W0 obviously exists. So we now define a positive number alpha. So alpha is defined as the minimum of W0 transpose x of n, where this vector x of n belongs to the subset H1. Now multiplying the W0 transpose on both sides of this equation 1, which we have taken this one. So we now get W0 transpose into W of n plus 1 is equal to W0 transpose x1 plus W0 transpose x2 plus so on W0 transpose x of n. From equation 2, for all these values, that is this value which you have taken, so this value is the minimum of W0 transpose into x of n. So where we take here this is alpha, that is x of 1, here we will be taking 1 alpha, this is 2 and so on up to n terms, right? So this we can write as W0 transpose into W of n plus 1 is greater than or equal to n alpha. Let us suppose that this is equation 3. So given two vectors W0 and Wn plus 1. Now the Cauchy-Squarz inequality states that the norm of W0 square and Wn plus 1 square norm is greater than or equal to W0 transpose into W of n plus 1 whole square. So now the norm of W0 square into the norm of Wn plus 1 square is greater than or equal to, so what is this value? W0 transpose into W of n plus 1 is greater than or equal to n alpha. So here it will be n square alpha square. So now solving this for the norm of W of n plus 1 square is greater than or equal to n square alpha square by W0 square norm. So now let us consider this as equation 4. So we will stop this solution up to this step. Now we go and follow another alternative route. That is, we take another development route. So taking this value. So now considering the equation A, which we have discussed previously, W of n plus 1 equal to W of n plus x of n. So we replace the values of n with k here. So we will be getting W of k plus 1 equal to W of k plus x of k for the values k equal to 1 to so on up to n, and x of k belongs to h1. So now taking the squared Euclidean norm of the equation 5. So here we have, this is the equation 5. By taking the squared Euclidean norm, so we will be getting W of k plus 1 square, the norm is equal to the norm of W of k square plus x of k square, that is the norm of x of k square plus 2 into W transpose k into x of k. So now our assumption is that the perceptron incorrectly classifies for the values k equal to 1, 2, so on up to n. So because the perceptron incorrectly classifies, we can say that this W transpose k into x of k is less than 0. So that is the reason we have written W transpose k into x of k is less than 0. So as W transpose k into x of k is less than 0, now the relationship between this W k plus 1 norm square and the right hand side values can be given as follows. That is, wk plus 1 norm square minus the norm of wk square is less than or equal to the norm of xk square. So where k is given by 1 to so on up to. So now adding the inequalities for k equal to 1 to n and invoking our assumption that w of 0 is equal to 0. So now what we will be getting? So we replace the k values with n because we are taking the k values from 1 to n. So w of n plus 1, that is the norm of w of n plus 1 square, is less than or equal to sigma k equal to 1 to n, the norm of xk square. Now let us again take a positive number beta. Now we assume that the positive number beta is equal to the maximum of the norm of x of k square, where this x of k belongs to the subset h1. So here we consider that the norm of w of n plus 1 square is less than or equal to n beta. So the bound we get here is w of n plus 1 norm square is less than or equal to n beta. So let us number this equation as equation 6. Now let us say that there is some value of n at n equal to n max, at which both the equations, that is the equation 4 which we have seen earlier, the equation 4 and the equation 6 are satisfied with an equality sign. So we get, so equation 4 is this one, right? So n square alpha square by w naught, the norm of w naught square is equal to n max beta. So given the solution vector w naught, solving for this n max, now what we will be getting? N max is equal to beta into w naught norm square by alpha square. So this is the upper limit on the value of n, that is beyond which there is no further updating of the weights. That is, by the point at n equal to n max, we have achieved a correct classification. We began with the incorrect classification, and now at n equal to n max, of course prior to the point of n max also, we have a situation where the incorrect classification is replaced by a correct classification. So this is the convergence we are aiming for. So we now state the fixed increment convergence theorem for the perceptron as follows. Let h1 and h2 be the linearly separable subsets of training vectors, that is the inputs presented to these perceptron have been originated from these two subsets. Finally, the perceptron converges after n naught iterations such that w of n naught is equal to w of n naught plus 1 is equal to w of n naught plus 2 is equal to, and so on for n naught which is less than or equal to n max. So we have already defined the value of n max. So for n naught less than or equal to n max, the perceptron is going to converge after n naught number of iterations. So this is all about the perceptron convergence theorem. Till now we have proved the convergence theorem for this perceptron by assuming the value of eta is equal to 1. So but for the variable values of eta also we can prove the convergence similarly. So this is all about the perceptron convergence theorem. Finally, we shall conclude our discussion on single layer perceptron by discussing some points. So we already know that we have discussed about McCulloch-Pitts neuronal model. So the perceptron addresses the drawbacks of McCulloch-Pitts neuron. That is, the perceptron can take the real numbers as inputs and weights, whereas the McCulloch-Pitts model cannot take the real numbers as weights associated with the inputs. And we know that the McCulloch-Pitts neuronal model is also not a truly machine learning model, but this perceptron model is a truly machine learning model which can be trained using the past data as we have seen in the previous slides. So now let us discuss some of the limitations of the single layer perceptron. However, in spite of these advantages, the single layer perceptron can produce only binary output. So we saw that the perceptron can be used only in the case of binary classification problems only, and also we saw that the perceptron can classify the data which is linearly separable. That is, if the data or the patterns are not linearly separable, then the perceptron cannot solve that problem. For example, we saw that the perceptron cannot solve the XOR problem. So these are the limitations of a single layer perceptron. So with this we have concluded our concept of single layer perceptron. Thank you.